Have you ever wondered how we get clean water from our taps? Or how gasoline is made from crude oil? Or even how that fizzy soda gets its bubbles? The answer, my friends, involves a lot of science, and specifically, a field called chemical engineering. Chemical engineers are like master chefs, but instead of food, they work with chemicals. They design and run the giant factories, called chemical plants, that make all sorts of amazing and useful products. It's a huge job, and it used to involve mountains of paper, endless calculations, and a whole lot of guesswork. But today, chemical engineers have a secret weapon, a kind of magic wand that helps them do their work better, faster, and safer than ever before. That magic wand is computational software. Think about it. Chemical engineering is all about change. It's about transforming one thing into another, like turning simple sand into the glass for your smartphone screen. These transformations, or chemical reactions, can be very complicated. They can involve extreme temperatures, high pressures, and materials that might be dangerous if not handled correctly. To manage all this, engineers need to understand exactly what's happening inside their pipes, tanks, and reactors. In the old days, they relied on books, charts, and their trusty slide rules to figure things out. Now, they can use powerful computer programs to see what's going on, almost like having X-ray vision for chemistry. This software is a fundamental part of a modern engineer's toolkit. So what is this computational software? Imagine you're building a model airplane. You have instructions, you have all the pieces, and you put them together step by step. Computational software is like an incredibly advanced set of instructions for a computer. It takes all the rules of chemistry and physics, things like how heat moves, how fluids flow, and how chemicals react with each other, and turns them into a program. An engineer can then use this program to build a virtual model of a real-world chemical plant. They can experiment with this virtual model, making changes and seeing what happens, all without having to build anything in the real world. It's a safe digital playground for some very serious science. This shift from paper to pixels has completely changed the game. It allows for a level of precision and understanding that was simply impossible a few decades ago. Instead of spending weeks doing calculations by hand, an engineer can get an answer in minutes. This frees them up to be more creative, to ask bigger questions, and to solve more complex problems. It's not about replacing the engineer's brain. It's about giving that brain a super-powered assistant. This digital toolbox helps them design the processes that make modern life possible, from the medicines that keep us healthy to the plastics in our toys. It's science, and it's really, really cool. Let's break it down. At its heart, computational software is a problem solver. It uses the language of mathematics to describe the physical world. Consider this. If you pour a glass of water, the water flows in a certain way. There are mathematical equations that can predict that flow. Now imagine trying to predict the flow of hot, sticky oil through 1,000 meters of twisting pipes. That's a lot more complicated. The software takes these complex mathematical models, which represent scientific laws, and solves them using the incredible processing power of a computer. It can handle thousands of calculations at once, something no human could ever do in a reasonable amount of time. So, what does this software actually do for the engineer? Well, it performs simulations. A simulation is like a virtual experiment. Instead of mixing two dangerous chemicals in a real lab to see if they explode, an engineer can mix them on a computer first. The software will predict what will happen based on the laws of chemistry. It can show the engineer how temperature will change, how pressure will build up, and whether the reaction is safe. This allows them to test ideas and designs in a completely safe and controlled environment. It's like being able to see into the future of a chemical reaction, which is a pretty neat trick. These programs are also used for something called process optimization. Optimization is just a fancy word for making something the best it can be. Let's say you have a factory that makes fertilizer. You want to make the most fertilizer possible, using the least amount of energy and creating the least amount of waste. That's a tough puzzle. An engineer can input all the details of their factory into the software. The size of the tanks, the temperature of the reactions, the speed of the pumps, and the software can run thousands of different scenarios to find the perfect combination. It helps engineers fine-tune their processes to be more efficient and environmentally friendly. Ultimately, this software acts as a bridge between scientific theory and real-world application. It translates the abstract principles you learn in a science textbook into practical, visual, and interactive results. It's not just a calculator, it's a dynamic tool that allows engineers to explore, design, and perfect the chemical processes that shape our world. It turns complex equations into colorful graphs, moving diagrams, and clear answers. It takes the what if questions that engineers always ask and provides them with solid, data-driven answers, making the invisible world of molecules and reactions visible on a screen. Let's look at a real-world example. Consider the process of desalination, which is turning salty seawater into fresh, drinkable water. This is incredibly important in many parts of the world. One common method is called reverse osmosis, where seawater is pushed at very high pressure through a special filter, or membrane, that only lets water molecules pass through, leaving the salt behind. Designing a desalination plant is a huge challenge. You need to figure out the perfect pressure, the right type of membrane, and the most efficient way to pump all that water. This is where process simulation software, like Aspen HYSYS or ChemCAD, comes in. It's a star player in the chemical engineering world. An engineer can use this software to build a complete virtual model of the desalination plant before a single pipe is laid. They can input the salt concentration of the seawater, the desired amount of fresh water, and the properties of different available membranes. The software then simulates the entire process. It will calculate exactly how much pressure is needed, which is crucial because pumping water at high pressure uses a lot of energy and costs a lot of money. The simulation can help the engineer find the sweet spot, the pressure that produces enough fresh water without using a ridiculous amount of electricity. This saves millions of dollars in operating costs over the life of the plant. Here's another cool example: computational fluid dynamics, or CFD. This type of software predicts how liquids and gases flow. Imagine you're designing a new type of reactor where you need to mix two chemicals together perfectly to create a new medicine. If they don't mix well, you might get a poor quality product, or even a dangerous side reaction. Instead of building dozens of expensive physical prototypes to test your mixer design, you can use CFD software. An engineer can draw their mixer design on the computer, and the software will create a beautiful, colorful simulation showing exactly how the fluids will swirl and combine inside. The CFD simulation can reveal dead zones where the fluid isn't mixing at all, or hot spots where the reaction is happening too fast. The engineer can then tweak the design on the computer, maybe change the shape of the mixing blades or the speed at which they turn, and instantly run a new simulation to see if their change fixed the problem. This process of virtual trial and error helps them perfect the design before building anything. This not only makes the process more efficient, ensuring a high-quality product, but it also improves safety by identifying and fixing potential problems in the design phase. So why is all this so important? The benefits are huge, and they touch on everything an engineer cares about: safety, efficiency, and innovation. First and foremost, safety. Chemical plants can be hazardous places. By allowing engineers to simulate dangerous reactions and test emergency shutdown procedures on a computer, this software helps prevent accidents before they happen. They can explore what would happen during a power failure or a pipe leak in the virtual world, allowing them to build safer, real-world plants with better safety systems. This digital foresight saves property, the environment, and most importantly, lives. It's a fundamental tool for responsible engineering. Then there's the matter of time and money. Building a chemical plant can cost billions of dollars. Making a mistake in the design phase can lead to incredibly expensive changes later on. By using software to design and optimize the plant virtually, companies can get it right the first time. Simulations help them choose the most cost-effective equipment and the most energy-efficient processes, saving vast sums of money on both construction and day-to-day operations. This efficiency doesn't just help a company's bottom line, it also helps conserve our planet's resources, like energy and raw materials, which is a win for everyone. Beyond safety and savings, these tools make work easier and foster innovation. They handle the tedious, repetitive calculations, freeing up engineers to focus on the creative aspects of their job, solving new problems and inventing new processes. A great idea for a new, greener way to make plastic can be tested and developed much faster with simulation software than with traditional methods. It lowers the barrier to experimentation, allowing more ideas to be explored. This accelerates the pace of technological progress, leading to better products, cleaner energy, and new solutions to the world's challenges. The software empowers engineers to be true innovators. For any student thinking about a career in chemical engineering, learning to use this software is no longer optional. It's essential. Just as a pilot needs to know how to fly a plane, a modern chemical engineer needs to know how to use these computational tools. They are the instruments you will use every single day to design, analyze, and improve the world around you. Mastering them will not only make you a more effective and valuable engineer, but will also give you the power to turn your scientific knowledge into tangible, world-changing solutions. So embrace the software, learn the code, and get ready to engineer a better future. Consider the following. It's science.